In this video, we will discuss how to calculate microstrain from XRD data using Origin. We know that an ideal crystal is an infinitely large and perfectly ordered array. From infinite here we mean that with respect to X-ray wavelength, few microns is considered as an infinite length. When we shine X-rays on the crystal, the X-rays go into the crystal through diffraction, and from the planes of the crystal, some X-rays are reflected to the detector that makes a diffraction pattern. However, when the planes of the same crystal shrink, X-rays deviate from its original position, and as a result, the whole XRD pattern shifts. While when a defect occurs in the same crystal, X-rays reflect at different angles from each plane and cause a broadening in the XRD peak. However, this broadening of the XRD peak is not only due to the sample but can also be due to the instrument. To get the actual broadening due to the sample, we will have to subtract the broadening caused by the instrument with the help of measurement of some standards. Broadening caused by the sample may consist of many involved defects of the crystal, which includes crystallite size, microstrain, solid solution inhomogeneity, and temperature factors. In this video, we will restrict to the microstrain only, which we define as the root mean square of variations in the lattice parameter across the sample. The features that contribute to the microstrain includes non-uniform lattice distortions, in which a distribution of D spaces exists compared to the ideal single D spacing. Faulting, in which the dominant is the staking fault. Fault contribution to the microstrain is HKL dependent. However, for an isotropic crystallite, it is HKL independent. Further, fault contribution to the microstrain depends only on the crystal structure. Dislocations. One of the main contributors to the microstrain and hence to the line broadening is dislocations, which has a strong dependence on the HKL. Antiphase domain boundaries. The boundary mismatch occurs during the formation of a material. It is to be noted that superstructure peaks are broadened while the fundamental peaks remain unaffected. Grain surface relaxation. Grain surfaces and interfaces in nanomaterials result in a residual stress, leading to the microstrain and hence to the line broadening. To calculate microstrain from XRD data, we will have to make sure few parameters, otherwise microstrain calculation will not be authentic. The very first one, we will have to make sure that XRD peak broadening is only due to strain, that is, crystal imperfection and distortion only. This can be ensured when microstrain decreases with an increase in 2 theta values. Crystallite size must be consistent over a long range of 2 theta values. We measure the microstrain by using the equation epsilon equals beta over 4 tangent theta. Here in this equation, epsilon is the microstrain in radians. As on this side, we have beta, which is in radians, and 4 tangent theta is a dimensionless quantity, so microstrain is also defined as the ratio of peak width to peak position, delta D over D. Beta is the line broadening at FWHM in radians. Theta is the Brake's angle in degrees, which is half of 2 theta. From XRD graph, we will take values of theta and will calculate the full width at half maximum, which is beta. To find the values of beta and theta, let me start with the origin file. This is the XRD data file of LIF. Let me plot this data. I will now find the position of peaks in full width at half maximum values. Let us go to the analysis, peaks and baseline, multiple peak and open the dialog. Pick the peaks by selecting with a double click. Open the non-linear fit. Click one iteration to see everything is good and then fit until converge. It will fit all the peaks. Click OK. So here I have fitted 4 peaks. Now go to the data under the nonlinear fit peak 1. Under the summary tab, these are the values of tau theta. Let us copy the values. Go to the Excel template where the microstrain can be calculated. This is the K value, the X-ray wavelength, and here are the tau theta values. Paste the copied values here. Now I will have to copy the beta values from origin. We can calculate the crystallite size with the help of Scherrer equation. In this equation, I can see that K and lambda are being multiplied. I will have to convert the beta values to radians, which are in degrees by default. We are having 2 theta values here, so I will have to divide it by 2 to get theta. As Excel by default calculates the trigonometric functions in radians, so we will take radian beforehand to finally get the value in degrees. The whole result is divided by 10 to get the value in nanometer as we have lambda in angstrom. Let us drag for the other values of the crystallite size for all the peaks. Now we can calculate the microstrain values. And here is the microstrain. I can drag it for the other values. As exponential minus 3 is with all the values, so I can take this as common as 10 to the power minus 3. We discussed earlier that there should be a decreasing trend in the microstrain values as the angle increases, so this is fine. But here the crystallite sizes are not consistent. They are decreasing as the angle is increasing, and this indicates that the crystallite size is also contributing to the peak broadening, and microstrain should not be calculated from such data, or the microstrain calculated from such a data will not be authentic. Let us check another XRD data. I will plot the data, and now again I will find the position and the full width at half maximum of these peaks. Go to Analysis, Peaks and Baseline, open the dialog and repeat the same practice. Peaks up to 70 degrees are sufficient. Click OK and go to the data. Here it has fitted 6 peaks. and the data is here under the nonlinear fit peak 2 in the summary tab. Let us copy paste the two theta and beta values in the Excel. Here I can see that the crystallite sizes are almost consistent with an increasing angle, so this is right. As another check, the microstrain should decrease with an increasing angle, so this data is perfect. And we can utilize the microstrain equation, and the values of microstrain will be authentic now. Thank you for watching the video.